Okay, let's see. Is my audio working? One sec, it's taking. Yes, it is. Okay, sweet. Let's go. Alrighty. So, looks like there are currently 7 people in here. Very good. That is a that is a good amount to start with. So, a little bit about what this live stream will be. I am going to be presenting just a very basic summary of this dissertation, an interpretation of relativistic spin entanglement using geometric algebra. Um, I will not be going into any of the relativistic stuff because, if I'm being completely honest, actually, I think the amazing part of this paper, like the part that gives you really, really good physical intuition, doesn't come from the relativistic stuff. It's actually from how it treats non-relativistic entanglement. And I think if you understand how the non-relativistic stuff works, then the relativistic stuff naturally just kind of follows. So I'm going to, before I begin, I would like to actually just read through some paragraphs here because I think they're pretty good. And then after that, I will begin presenting or some summaries using some notes that I have written up here, and then I will present them using my iPad, which I have connected. Alrighty. So let's get to this paragraph that I wanted to read, and that is: by interpreting entanglement or any other superposition as a collection of possible transformations, weirdness no longer needs to be attributed to quantum states themselves. Instead, it is the probabilistic happenings which are in superposition and can be discussed in terms of the probabilities of being yet to happen or even of having happened already. The present work argues that such an interpretation involves markedly less weirdness than superpositions of states of physical systems. So the idea is that the results that we'll get from this paper is that rather than the physical system being in a superposition of different states at the same time, rather it's a statement that the system is transforming in a way that is unknown to the observer. And so the observer can only describe it as being in a superposition of transformations, and the observer will never observe which one it is until the observer interacts with the system. And so rather than the probability or the probability being like some kind of collapse, it's more like a statement of relational information. And that's why this actually like naturally leads to the relational interpretation of quantum mechanics. For those who are familiar, I really recommend reading up more on relational quantum mechanics. It's very cool. All right, let me get this over here, move my mouse, and then get my iPad ready. So yes, it looks like my iPad is indeed connected. So let's. Ooh. Oh no. Okay. Whatever. Just showed stuff that I think it should be fine. I accidentally hit the enter key and that messed everything up. Okay. There we go. So first off, let's do a little bit of summary of the algebra of physical space. So that is a geometric algebra. So this paper, this paper and feel free to ask questions in the chat. I'll try to, or no, I'll try. If I see them, I'll answer them. They're right in front of my face, so I don't know how I'd miss them. It uses the geometric algebra G3, which we can define as the real numbers extended over the basis vectors in the x, y, and z direction. I use the sigma x for notation for my basis vector in the x direction, sigma y for the y direction, and sigma z for the z direction. The reason I do this is because the Pauli matrices serve as a matrix representation for this. And so for those of you who are maybe more familiar with matrix algebra, the geometric algebra of three-dimensional space, also called the algebra of physical space, this is isomorphic to the 2x2 complex matrix algebra. But we're not going to be dealing with this, we're going to be dealing with this. So let me just put the name of this algebra for everyone to see. And that is the algebra of physical space. There we go. So that's what this paper is going to be using. So something very interesting about this is that it's very standard to split basically the number 1 into 2 different elements. So let's see how can we do this, and why is this even related to what I'm about to be talking about. So say I take the number 1, then I can basically split the 1 into 2 1/2s, and then I can add 1/2 times sigma z, and then I can subtract 1/2 times sigma z, and this is still equal to 1. But I can now regroup these, adding this to this and this to this. So I get 1/2 1 plus sigma z, and then I get plus 1/2 1 minus sigma z. And again, this is the number 1, and then this is the basis vector in the z direction. Number 1, basis vector in the z direction. And we call these two elements projectors or idempotents. They have the property that f plus or minus squared is going to be f plus or minus just itself. So it squares to itself. That's why it's called idempotent. Idem meaning like identity, like potent. So it's it is its own potential. It squares to itself. So the traditional way of doing quantum mechanics or relational mechanics or entanglement mechanics here is to actually identify this f plus here with spin up, because now you've broken identity into 2 different components, and you can say that this component right here is going to be the component that is spin up, and you can say that this is component spin down, but that's a little more nuanced, and we'll see why that's the case in a little bit, because rather this is the spin up like density matrix, and this is the spin down density matrix, but you'll see that the spin up state and the spin up density matrix are linearly related. Basically, they're equal. So we can identify with the spin up state. Spin up state. And why can we identify it with spin up? Because it might seem a little weird that we can just kind of break 1 up into these 2 arbitrary numbers and be like, yes, that's spin up. That seems completely random, and like there's no reason why to do it. The reason actually comes from some relativistic mechanics in the algebra of physical space, and that is that the unit 1, the number 1, represents the time-like direction. And so when you break up the unit 1 into these 2 different things, you've now broken up the unit 1 into some time plus some spatial component, and they have the same component. They have the same what do you call it? Coefficients, and so they increase in lockstep. If you increase in time, you're going to increase in space at the same amount. And something that increases in time and space in the same amount, I can draw this right here and right here. So let's say that this is space and then this is time. If they increase in the same amount, then you're going to have a diagonal, and this is exactly a light ray. And light rays are kind of used as a way to have orientation. And so we can define the spin-up state as this light ray that is associating with, as I increase time positively, I continuously have a positive orientation in the z direction. So this light ray is a geometric and mathematical way to identify these spin, or like to identify an orientation. And because we associate spin with an orientation, these two concepts mesh together. All right, so we can define this F plus as spin up. So we can define this spin up ket then. I'll just call this F plus. Now we want to figure out what the down ket is, what the spin down ket will be. Well, let's imagine this. If we have an object in the algebra of physical space, and we have something called a rotor. So spin 3, and for those who are more familiar with traditional spin stuff, you have SU2. So SU2 is, of course, going to be the Pauli spin group, and that's just isomorphic to spin 3, and spin 3 is the transformation group of G3. This naturally lives within this. So we have this rotor, then how do we actually transform an object, a physical object in the space? Well, actually, we just map G, we transform it by saying we have this rotor times G times the inverse of this rotor. And this is the reverse operator. So for those who are perhaps needing a reminder of this, if you have A, B, C, and I take the reverse of A, B, C, then I get C reverse, B reverse, A reverse. Okay, so we're basically going to do the same exact thing, except we are now only going to consider a single-sided transformation. Now, why would I do that? I've just shown that a general object transforms with an application of a rotation on both sides. So why on earth would I only want to consider a single side? And that's because if I change R, I automatically change R dagger. And so in considering the system's transformations, I don't actually need to consider the entire like geometry. I only need to consider a single R to understand the behavior of the entire system. So in a sense, a single R parameterizes the behavior of the entire object. So in order to do that, I'm going to then say, well, I'm going to define a rotation that's going to rotate 180 degrees. So it's going to be an exponential of 1/2 pi. So pi is the angle that I want to rotate by, and then I want to rotate in the zx plane. And then again, this factor of 1/2, for those of you familiar with geometric algebra or even the SU2, you get the factor of 1/2 because in the total system, you're rotating by 180 degrees. And so you need a factor of 1/2 and 1/2 here because the total angle will add up to pi. But again, because we are parameterizing this and we're only looking at a single one, we only need to consider a single rotor, and so we keep the 1/2. And so this is the reason why people are like, oh, well, electrons are weird or fermions are weird, because if I have to rotate by 4 pi to complete a full rotation here. Well, that's not really what's happening. It's more that the R here, this rotation, parameterizes the entire rotation, but it does it with a factor of 1/2. So it's just that the behavior, the physical behavior is going to come from this, but the algebraic behavior is just going to have a factor of 1/2. It's going to kind of like um, not slow it down, but it's going to make the behavior look weird, even though in reality this is still representing a 180-degree rotation. So let's just expand this. So it's going to be pi over 2, and then it's going to be minus 1, or no, not minus 1/2, minus zx sine pi over 2. And this is just going to be equal cosine of pi over 2. That's going to be 0. Sine of pi over 2, that's going to be 1. So we get, this is minus sigma z x. And because this anti-commutes, we can rewrite this as sigma xz. So the minus sign is now absorbed into this by switching the labels. So this implies that I can then perform a pi rotation on the spin up state, and that's just simply going to be sigma x z times this f plus, and then I'll expand this out fully. So you have 1/2, you're going to have sigma x z, and then you're going to have plus sigma x z times sigma z, and this is just going to be 1/2 sigma xz plus, and then the sigma z's, these square to 1, so you just get sigma x. And now I can just pull out this sigma x again. So I have 1/2 sigma x, 1 plus sigma z, and this is just going to be equal to sigma x f plus. And so this is what I'm going to define my spin down ket as. So sigma x f plus. You can see that it's really not just it's not an arbitrary thing. It's that I'm taking the spin up state and then I'm applying a 180-degree rotation, and that's going to rotate it down to my spin 1/2. Okay. So now we have that, and let's put a little reminder. It's not necessary to do this, but I'm just going to write out the Pauli representation. So for those of you who do like matrices, Pauli matrix representation. So for the spin up ket, which is just going to be F plus, this is represented by a matrix with a single entry up here, and this is equivalent to just a column matrix like this. So you can see kind of why this represents the spin up component in what people traditionally do for quantum mechanics or for entanglement mechanics, because they usually say, okay, well, they have a 2-bit system. I'm going to say 1 here, 0 here. But it turns out that this math or algebraically is equivalent to just having a matrix with a single entry. And that is algebraically, or this is the matrix representation for F plus. So you can see like these, it's all the same thing. It's really all the same thing. Now let's do this for the spin down as well. Sigma x F plus, its matrix representation is going to be 0, 1, 0, 0. And that's, as you probably guessed, equivalent to a column with 0 and 1. Cool, cool. And again, I'm hoping for people to ask questions here, because I am presenting this like assuming a fair bit of background knowledge, and I'm totally open to, like, if anybody asks questions, I'm totally open to just like explaining, going back on and explaining little bits and pieces so that things are more understandable, because I realize that there's kind of a lot that you need to know before this to be able to to fully grasp everything. And I might not have presented. I definitely did not present everything, so it would be really great if people ask questions. Okay, so now let's consider what a general state would look like for a particle. So if we have, or I'll just say this, general, I'll say this, general spin state. And you'll see that I actually try to refrain from saying state when I'm talking about this, and you'll understand why after I finish presenting the interpretation that this paper presents. Because the idea of states actually become less important once you understand the importance of transformations. But for now, because that's kind of, it's still standard and it's easier to relate this to people who know the standard approaches, I'm going to just call this a general spin state. So if we have some general rotation, then we can represent some state psi as just a rotation on the spin up state. And for the rest of this video, I'm going to call the spin up state the rest frame. So the particle sees itself as being spin up, but then the actually observed value is going to be given by the rotation applied to what the particle sees itself as. Okay, so this then, oh, if F plus is spin up state and sigma spin down. Yes, okay, good question. With the F minus, I will be talking about that in a little bit. So that comes up when we consider the density elements. So that's why I didn't talk about it. I kind of introduced it, but then I didn't speak about it much. That's a good question. You'll see it in next page. Yeah, next page. So 5 minutes or so. Also, what's my iPad percent? Okay, I have more than enough battery. Sweet. So this rotation is going to break it into two parts. So I'm going to call it the components that spin up times the spin up ket plus the component of spin down, and then the spin down ket. And this is going to be for the R up or down. These are going to be, so I'm going to write I'm going to write a big mess right here. It's going to be in what's called the center of the algebra. And this center turns out to be just the scalar and the pseudoscalar subspaces. And this is just going to be isomorphic to complex numbers. So what I did with writing in all of this mess is I'm saying that these naturally, in the algebra of physical space, these naturally become complex numbers, but not in the sense that they're in the complex algebra, rather that these numbers will live in a subset of the algebra of physical space called the center, and that this subset that naturally exists there is isomorphic to complex numbers. And so you get that actually complex numbers kind of fall out of the mathematics, fall out of the algebra. So we don't need to invoke um, complex numbers for spin mechanics, which I think is pretty interesting because some people might be a little confused. Oh, why do we have complex numbers here? It doesn't make sense. This is kind of the reason why. It just falls out of the geometry. Okay, so now we have that. Now let us talk about state density elements. So we now have this is a spin state, and then I'm going to call this I might as well just write it out fully. Density element. Yes. Yeah, the center is that it commutes with all other elements of the algebra. Yeah, that's correct. I probably should have said that. So, spin state density element. Now, we just say that for a particular spin, or for a particular state, we have the density element rho, which is just going to be whatever the state is, its ket times its bra. And we can now plug in, we know that it's just defined as R spin up, and then plus R spin up, like this. And now I can plug in the values. I can plug in what I know these are. So the bra is just the Hermitian conjugate, or the reverse. So I get that this is just R F plus, and then F plus reverse R reverse. But this is just going to be R F plus R reverse. And now if I expand this, we're going to get R dagger, that's its inverse, plus R sigma Z R dagger. And this is just going to be 1/2 1 plus S hat. So this right here is the definition of the spin vector. It tells you the spin orientation of your state. Again, I'm using state with the air quotes, but this is what a density element is. So I already spoke about how The F plus is an orientation by saying that you have some kind of space, time, they increase in lockstep. And so that's a way of saying that how a light ray can represent a kind of like permanent orientation, or consistent orientation, not permanent. Then this is exactly the same thing. It's just that now you have an orientation that is not in the sigma z direction necessarily. You now have something that's in the just more general S direction. So geometrically, this still represents a light ray. It's just now that it's pointing, instead of in your sigma z direction, say like that's the spin direction, it's now pointing in that direction. Okay. All right, so now let's talk about systems of states. So systems of states. Or system of states. So there's a system density element. And this system density element, I'm just going to write rho system, is going to be the sum over J of just your J different states, creating their different density elements. So it's just a sum over all the density elements, like this. So a system is said to be in a pure state if it is completely, or if it is theoretically possible to completely specify the state. And what that means in the algebra of physical space is that a pure state is a system wherein is a state wherein the system is just a rotation from a spin-up state. So this is a pure state. But if you add many, many pure states up, you're going to get impure states or mixed states. And this would be the equation that tells you how to add them up. So let's just give an example of a pure state and an example of a mixed state. So if your rho system is just going to be like, say, literally just 1 plus s hat, that's a pure state. But if we have, say, rho system, and if we define it as some component alpha times f plus, and then some component beta, f minus, this is a mixed system. And so now you're finally seeing where f minus comes in. This right here is actually an ensemble of having alpha. You have the probability alpha of, or not probability, you have the percentage of your system alpha that's in a spin up state, and you now have a percentage beta of your system that's in the f minus state. And so it's common to rewrite these as alpha rho up plus beta rho down for the cases that, or for alpha plus beta equal 1. And so I'll just rephrase this now. Alpha and beta tell you the way that your system is split into different spins. So if you can define your spin up density to just be f plus. And then you can say that the percentage of that say system that's in that state is then given by alpha. And then you can say that I now have a spin down density element, and that's going to be given by f minus. And the percentage of the system that's in that is going to be given by beta. And so that's what f plus or an f minus are. So that hopefully is more of an answer to your question. Okay. So now we kind of have all of the background that we need. We're not going to be talking about density elements anymore, but this was hopefully enough just to give a conceptual understanding for the next step that we will make. So now we're going to actually get into talk about entanglement. Yes, alpha and beta are real scalars. Yeah. No, because I guess I should have specified that. Alpha beta real, just because it makes no sense to have a percentage given by a complex number. There we go. So those are real. All right, so now we're going to be talking about something called bipartite states. And this is where entanglement can actually be seen. Bipartite states. So for, say we have n particles. So if we have an n particle system, then the total spin state configuration, so I'll say this, n particles, spin state configuration we're going to have that your total ket system is going to be your first particle, the state of your first particle, tensored with the state of your second particle, and so forth until you have your nth particle. So this is for a system of n particles. But we will be doing stuff, what's called bipartite. Bi means two. We're going to have two particles. Two particles. And that is going to look just like this. It might be redundant for me to write this a second time, but we're just going to have C1 tensored with C2, like this. So we have a system of two particles. Now, let's review a little bit of the algebra of having tensors, because this is still geometric algebra. It's just now, we're now considering a geometric algebra tensored with another geometric algebra. So in a sense, the tensor product really represents the fact that, like, I'm considering two subsystems. That's really what the tensor product is doing. It's saying that, okay, I have one particle, I have another particle, but they are correlated. I want to consider them at the same time. I'm going to glue them together. That glue is the tensor product. Okay, so let's do a quick recap of how tensor product math works. Quick recap. So let's consider, say I have a multivector G1, tensor a multivector G2. So G1 lives in the first geometric space, G2 lives in the second. And then I'm multiplying by another multivector H1 tensored, another multivector H2. So they both live in two separate spaces. How do these interact? Well, the separate spaces are separate. They don't interact. So we have G1 times H1, and then that's tensored, that's a bad tensor sign, that's tensored with G2, H2. That's it. So that's how we have products interact. It's pretty simple, but it makes sense conceptually with the idea of having two separate subspaces. The two separate subspaces are separate and interact separately. And this is just a mathematical way to write that. So this implies something very interesting. We can now factor. So this means we can factor our system into correlated rotations of a correlated rest frame. And again, I'm using the term rest frame to mean spin up, like the particle sees itself as spin up. Okay. So correlated rotation just means that the rotations are there's information that is related between the two, correlated rotations. So we can describe our system here as just the tensor product, again, between two others. Now, I also want to just give a quick statement about all of this. These do not necessarily mean entangled. You cannot write, actually, by definition, you cannot write an entangled state like this, and so these do not all give entanglement, as we'll see shortly. But I'm just using this as a motivation for some of the mathematics that we will use when we actually deal with entangled systems. Okay. So C1, C2, we can just break these into rotation 1 times up, and then some rotation 2 times up, and then I can break them into their two separate elements. There we go, and I will simplify this by just writing R12 and spin up, up. So this is not an entangled system. However, this exact mathematical approach that I just did, where I broke up the system state into basically a correlated rest frame times some kind of transformation, this is something we can do in entangled states. And so I wanted to show it for a non-entangled state so that I can show it for an entangled state. So then how does that work? How do we find entangled states? Well, let's first define an actually general pure system state. So general pure state system state. That can be given as C system is going to be some alpha up up plus some beta up down plus some gamma down up plus some delta down down. And this is 4 magnitude of alpha squared plus magnitude of beta squared plus magnitude of gamma squared plus magnitude of delta squared equal to 1. So a normalized state. So an entangled state means it cannot be represented in the form C1 tensor C2. That's really what entanglement means, is that you cannot represent something in the form here. But we can calculate how much something is entangled using this equation right here. So, before I go on, actually, I just want to clarify something that I think I already actually clarified. Never mind. I already talked about it. So, let's talk about actually calculating entanglement. So, calculating entanglement is done via concurrence. So concurrence is just a scalar function of your state, and it's going to be 2 times the magnitude of alpha beta minus gamma delta. So this is what concurrence is. And for the cases when C is equal to 1, then we have maximum entanglement. Maximum entanglement. For the cases when C equals 0, we have minimum, which is 0 entanglement. So what are the cases that maximize entanglement? So cases that maximize entanglement. That is going to be, let me just copy this. That is going to be when alpha, the magnitude of alpha equals the magnitude of beta, which is equal to 1 over the square root of 2, not equal to the magnitude of gamma, which is equal to the magnitude of delta, which is equal to 0. Or we have the magnitude of alpha is equal to the magnitude of beta, which is equal to 0, which is not equal to the magnitude of gamma, which is equal to the magnitude of delta, which is going to be equal to 1 over square root of 2. So we have 2 distinct possibilities for maximum entanglement here, but we are applying that to a total of 4 different bases, and so we actually get that there are 4 possible maximum entangled states. So from this, there exist 4 unique up to a phase, maximally entangled states. And these are, I'm going to write them as A plus minus, and that's going to be 1 over square root of 2, down, up, plus or minus, up, down, and it's going to be B plus or minus equal to square root of 2 over 1 over 2, up, up, plus or minus, down, down. So you'll see that I constructed these from the general case here, and I set gamma delta equal to 0. So gamma delta equal to 0. Oh, hang on. I think I wrote, yes, I did write these wrong. So the delta should be gamma beta, not delta. And then the alpha, delta, beta. That's my bad. So I have this one where gamma and beta are equal to 0, and that's going to give me this case. And then I have my alpha delta equal to 0, and that's going to give me this case. So there are 4 unique maximally entangled states. And these are the Bell, let's call it you can call it the Bell basis or the Bell states. And it is completely possible to rewrite this as a combination of these Bell states. So just in general, you can rewrite a general pure system state decomposed by the Bell states. But it's not what we're going to do. We are going to use this, where we saw that we could factor our system into some kind of correlated rest frame and some form of transformation. And now we are going to do that for the Bell states. And why are we going to do that? It's because if we can do that for the Bell states, we can move all of the entanglement that is held by the states into the transformations. So the transformations will hold all of the entanglement information. In maximally entangled, oh, here, I'm just seeing a question. In maximally entangled states, particles have either same or opposite spin projections. So you mean in the maximally, so like if you're in one of these two Bell states, well then like in the traditional way of thinking about quantum or about entanglement mechanics, then you would look at this and say that, okay, my system is either both spin up or both spin down. But if you were in this entangled system, then you'd be like either it's down up or up down. So yes, those are like for these two different subcases of Bell states, then yeah, maximally entangled states, you either have opposite spin or yeah, same spin here. But we're going to try to move away from the idea of thinking about relational mechanics in terms of states with the following. So note our earlier statement that system states may be factored into correlated rotations. So I'm just going to write this all out. Note our earlier statement or finding, I'll say that, our earlier finding that system states may be factored into correlated rotations of a correlated rest frame. So it's possible to rewrite, so we may rewrite the Bell states. So we're going to first identify the following in this rotation in geometric algebra. So we're going to say that R0 is just 1. This is the identity rotation in spin 3. So this is the rotation that does absolutely nothing. Identity rotation. Very cool. And we're also going to have our R pi that we defined earlier, but I'll just rewrite it for the sake of people here. Sigma zx, and this is just going to be sigma xz, like so. So we have these two rotations, which they are in spin 3. And using this, we can see that if I apply R0 to spin up, so I'll do this, I'll say spin up or spin down, it's just going to be equal to spin up or spin down. And if I apply R pi to spin up or spin down, then I get spin down or spin up. So it flips them. So we're now going to use this fact. So let's copy and paste the first Bell state right here. So 1 over square root of 2. And now I'm going to write this in terms of its explicit rotations. So it's now going to be rotation of pi acting on spin up, tensored with rotation of naught acting on spin up, plus or minus a rotation of naught acting on spin up, tensored with a rotation of pi acting on spin up. Man, I'm really writing slanted today. That's crazy. So we have that. And now I'm just going to, because everything here has a factor of spin up, I'm going to now factor that out. So I get 1 over square root of 2. And then just before I write everything in here, I'm going to just factor this out. So I get up, cat like this. Well, then all I'm left with here is r pi tensored with r naught plus or minus r naught tensored with r pi. And indeed, this is of the form some kind of transformation, which I'm just going to say it's the a plus or minus transformation, acting on a correlated rest frame. And so, no longer is the entanglement information actually held in the states. It is held completely within this transformation. So this also gives us a reason why we can say that we didn't have entanglement here. So why didn't we have entanglement in this state right here? Well, look at this. We have the spin up, but then we just have R1 and R2. They're not related to each other at all. They're correlated, but they are also not, what do you call it? They're correlated in the sense that they're attached to one another, but a decision made here doesn't make a decision here. Whereas this rotation could either be we're rotating the first one by 180 degrees or doing nothing, or it could be we're doing nothing and rotating by 180 degrees. And so there's no way to know between the two. And so rather than thinking of entanglement or superposition as the state being it's both in spin up and it's in spin down at the same time, instead of saying that, this is saying that both particles see themselves as spin up, but the relational information between the two, there are two, or it's basically saying there are now two possible ways to relate the particles' correlated rest frames. There are two possible ways which are impossible to distinguish until they are interacted with. And so rather than saying that the particles are in two separate, or they're in a superposition of states, they're in spin up and spin down at the same time, it's saying that the rotation, the act of rotation, is in superposition itself. And then there's going to be a paragraph from the paper that I'm going to read that summarizes it way better than I am right now. So I'll just read that in a little bit. But now let me just do this exact same thing, but for the other two Bell states, just to reinforce the point I'm making. So to show that we indeed can do it a second time. So we know the second Bell state is this. And now I'm just going to break it into R naught acting on up, tensored R naught acting on up, and that's going to be plus or minus R pi acting on up, tensored with R pi acting on up. So let's factor this out again. Yes, yeah, no, that's cool, Leo. Like, it is really interesting. It's a simple rewriting, but completely different interpretation. And I'm forgetting what it was, but I was speaking with someone the other day, and they were saying that there's some I can't remember what it was. They were doing it's something in the Dyson expansion. They're saying that like there are some quantum systems where you're doing like Dyson expansions, and it doesn't make sense to think of things as in superpositions of states, and it makes sense to think of them as in superpositions of transitions. Which naturally like is another like reason to kind of believe the interpretation given by this rewriting. So it's something that's super cool. Um, all right, so now I'm going to just finish this. I can factor out the up, and then I'm just left with R naught tensor R naught plus or minus R pi tensor R pi. And then this could just be 1 over square root of 2 R, what do you call it? No. Just R B plus or minus acting on spin up, spin up. So again, we can describe all of the entanglement information as being contained within this transformation that relates the two correlated rest frames. So yeah, that's the really cool part about all of this. And I think that like the paper doesn't talk about this, but there are some natural generalizations I think that come out of this. Like you could probably describe some kind of like correlated state as like you could probably do something like this where you're like I have like rotation, some just general rotation 1 tensor rotation 2 plus or minus some other rotation 2 tensor some rotation 1. And you could probably describe stuff more generally like this, and this would be an entangled state, but it wouldn't be, you could have it for arbitrary directions, so you wouldn't have to specify like a what do you call it, coordinate system or other things. It's just it'd be neat little things like that I think that there are many things that could be done to extend the research that was done in this dissertation, but that's for another day and for people that are not me and that have more time. But now let's read the parts of the paper that I wanted to read. Okay, so it's really these three things. So to compare the physical interpretation of entanglement as a transformation and entanglement as a state, note that both still describe probabilistic information about possible measurement results. But as a transformation, it may be described in a more atemporal way, meaning you don't need to actually specify like this happens before this happens before that. Like the states are in this position before they collapse. So you don't need to think about time as being part of the process. So specifically, entanglement as a transformation can describe equally well the probabilities for a transition yet to take place, and also the probabilities of which transformation has taken place, but with the information not yet available to the observer. Although this work is restricted to describing the entangling transformation as a superposition of rotations of a spin state, the general idea behind the interpretation may be applied to more general situations involving superpositions. For example, the state of Schrodinger's cat need not be described as half alive and half dead, because it may instead be interpreted by the observer as alive until proven otherwise. After all, it is only the transition, the probability of death happening, that is in superposition. If the death has taken place and the observer is unaware, the superposition does not change because there is no need to distinguish between the probability of death happening and the probability of death having happened. Because as I said before, it's kind of in a more atemporal way. And so it's more about the results and then like the states collapsing to some other possibility. So, um, yes, having happened not until actively interacting with the system to check the result. So, by interpreting entanglement or any other superposition as a collection of possible transformations, weirdness no longer needs to be attributed to quantum states themselves. Instead, it is the probabilistic happenings which are in superposition and can be discussed in terms of the probabilities of being yet to happen or even having happened already. And then this interpretation bypasses the idea of spooky action at a distance. Instead, the collapse of the wave function simply represents the revelation about which relative rotations ended up describing the particles in question, which is information that can only be attained after the measurement takes place. So Yeah, I think that's kind of it. One of the interesting things about this is that first off, it's kind of well known in the particle physics community that spin is not a quantum phenomenon. But in outside of that, like people don't really talk about spin as non-quantum. They think of it as only a quantum feature. But in reality, spin is a classical element of reality. And so it's actually very common for people to view entanglement as a quantum only phenomenon. But I think this is just an extension of the logic that is held in particle physics communities, which is that these spin mechanics, it's not quantum mechanics, it's information relations, informational mechanics, or relational mechanics, whatever you want to call it. And so the quantum mechanics comes about later when you actually are dealing with like uh, it's more complicated. I won't get into it now, but it's just really interesting. Um, yeah, it's just when it comes down to it, it's kind of all relational mechanics. This is I've presented everything I need to. I'll give the next little bit. I'll wait for questions to come up because this was a lot of information in a short amount of time and a lot of rambling in between. So I'll wait a few minutes for questions. I'll wait 5 minutes. I'll wait exactly 5 minutes for questions, and then if there are none, then I will end the stream. And those 5 minutes will just be me staring awkwardly at the screen. Actually, I don't know what about want to wait 5 minutes, man. It's a long time. How about this? I don't have a clock app. Okay, interesting. Looks like no questions, so I will just go. Well, thank you for watching. I appreciate all of the people. I actually had more viewers than I was expecting, so that was cool. Thank you for the questions during it so that I could clarify some things. Other than that, that's it. Bye.